In this section, we're going to learn about the conic sections, and much of this might just be a review for you from trigonometry, but that's okay. These are a very important topic that have applications in lots of different fields of mathematics and physics and other fields of study as well. So let's take a brief look at them. So the conic sections are a set of curves that can be produced by intersecting a cone. Well, in fact, two cones on top of one another, intersecting a cone and a plane in space. So this illustration kind of shows you here, but let me show you something that's a little more interactive that we can visualize better. Okay, so here I have a three-dimensional rendering of two cones stacked on top of one another. And then lying flat in the XY plane is a blue plane that I can manipulate. So right now, it's just cutting through the center of these two cones, so nothing really particularly special is happening. But if I were to raise the level of the plane, then the place where it intersects with the cone is going to make a circle. So a circle is a type of conic section. If I were to tilt the angle of the plane, so here I'll just tilt it a little bit, you can see that that tilt actually then the intersection between the plane and the cone produces an ellipse. So an ellipse is a type of conic section as well. So any figure that you can make from the intersection of these two items creates a conic section. If I were to continue to increase theta beyond the side angle measure of the cones themselves, then the plane would eventually come out the other side. And in that situation, we have a parabola that's created. So I'm trying to get that to lay on 50. There we go. Anyway, you can see the shape of the parabola here that's produced by intersecting the plane and the cone now. And if you continue, eventually the plane will run into the cone at the bottom and produce the type of conic that's known as a hyperbola. So it kind of looks like two different parabolas sitting on top of one another, but they're a different shape altogether. And so that intersection's shape is known as a hyperbola. And we'll investigate each of these separately throughout this section. So this just kind of gives you an overview of where these things come from. And just to mention, I generally will get a question or two about what happens if you allow the plane to pass through that middle point. Does a line count as a conic section? Well, we typically don't count a line as a conic section, but it does fit most criteria of a conic section. Generally speaking, if it's considered a conic at all, it's considered what's known as a degenerate conic section. The same thing for a point, because if I had this plane just lying flat, 0-degree angle here, if I can reach it, and passing right through the center, really they're intersecting at just a point. But again, a point, we don't really consider a point to be a conic section, even though it would technically be considered a degenerate conic, like a line. Now, as I mentioned, conic sections are really important types of curves because they show up in so many different applications. So in example physics, parabolas describe the path of projectile motion. Ellipses describe the paths of planets around the sun. And these are just two of a myriad of examples that are available within physics applications. In architecture, parabolas are known to be the strongest structure and can be found in many different examples. Now, let me show you a few. So here's a first example, and though we're not actually looking at directly at parabolas, you can kind of see, an idea of the arch. And the arch is similar to shape in parabola, and what it's able to do is uh, help hold the weight load above it and distribute that weight load to the stronger pieces outside. And so you have this empty space in between that doesn't contain any bricks, and you're able to construct a building upward that way. If everything were straight across like this one, it wouldn't be quite as strong, and it wouldn't be able to hold up the uh, building above it, which is probably why you see that at the top of the building, but not toward the bottom. Here's another example from antiquity. This is the Pantheon in Rome as well. And this building has survived, I think, around 2,000 years, maybe longer than that. And the reason that it survived, sometimes it's a little difficult to see, but I picked a picture that actually depicts it pretty well. The general brick structure contains these arches within it. Right, so you have all these bricks going laterally on the inside of these arches, and really, I mean, I'm sure they're contributing, but I don't think they're contributing much to holding the weight of the roof. I think most of the weight is being distributed to these arches, this sequence of arches around, and they're kind of built into the structure. So builds in a lot of strength because it disperses the weight down to larger columns or lower sections. And you can see those sort of built into the structure in different places here. It's not just right there. But what's odd is that they weren't really designed, I would think, as an aspect that is to be shown off, because otherwise in my opinion, they probably would be a little bit more ornate. There may have even been some type of material on the outside of these bricks at some point, but I don't know the history of the building that well. So anyway, the point is, these properties of the conic sections have been known for millennia and been used for that, at least that amount of time. And so they're very important and definitely worth looking into. Now, some examples with more modern architecture. Here's an example if you're taking this class in the Charleston area. This is the Music Farm. And the Music Farm is this very large brick facility. And if you'll notice, there's really no support beams, like in the middle of the building whatsoever. So this huge width of building is held up by its support in the structure of the roof. And if you look at that support structure, it includes parabolas, okay, but not only that, but it has parabolas here that have been extra reinforced with cross beams like this in the form of X's, which make triangles, which are another extremely strong, rigid object in architecture. So we can get, even with wood beams, we can get extremely large ranges of spans for roofs with a material as weak as wood. So taking advantage of the shape really increases our ability to build something unique. Now here's one last example, which is probably newer than the Music Farm, but this is located in West Virginia. This is a type of bridge that takes advantage of, again, a parabola for its main structure. And all the weight of this bridge is brought down to that structure through vertical beams. but everything on top ultimately rests upon this parabolic arch. It again is reinforced with triangles, but that arch being being the strongest uh, form that you can create architecturally, really allows a bridge of this width to be carried on. Ultimately, just like there's a part right here and down below over here where it connects to land. Most of the weight is carried by those two instances. So another thing that is interesting about conic sections is that they all can be expressed in a general equation that relates all conic sections. So the general form of a conic section looks like this right here. The equation ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. So a lot of coefficients there, but this encompasses a lot of different types of curves. So bxy, you don't often see at this level. It's a rotational term, and we generally disregard it at this level. But if you wanted to create the equation of an ellipse that is angled by 45 degrees, for instance, then you would use that rotational term. But the other coefficients we will need to learn and be able to use pretty readily. And the first thing that we are going to learn how to do is identify which type of conic we're actually looking at simply by observations of the general form equation. So if we look at the two most important variables, that's going to be a and c. These are the variables on the squared terms. And if these two variables are equal to one another, then this conic section is very likely going to produce a circle. Now, it's entirely that something strange happens and it produces just a point, which is a degenerate conic, or it ends up producing, some type of object in the complex plane. But in general, we can assume that the relationship is basically a circle. If these two terms are not equal to one another, then the conic would form an ellipse. If one of those two terms is 0, all right, but not both, then we would end up with a parabola. So we'd only have one squared variable in that equation, and that would produce a parabola. If both variables that were squared were missing, we would effectively have a line. All right, then if the product of those two, if it's less than 0, then we're going to end up with a hyperbola. So there's kind of a caveat to the ellipse one. And you want to be careful because, if the value of a and c are the same but differ in sign, it would still produce a hyperbola rather than an ellipse. Both a and c can be negative, and it could still produce a circle, although it might produce, a point or some non-existent value in real numbers. Let's take a look at a couple of examples and see if we can identify some conic sections, and then you can try some in your homework. So identify the type of conic described by these equations. So in the first one, just going through and observing what we have here, we have one squared variable. All right, so if there's only one squared variable, then that is a pretty good indicator that this would produce a parabola. And actually, that's better than a pretty good indicator. That is the indicator. In the next one, I have both terms are squared. All right. I'm not quite in the form of in general form here because in general form you have everything on one side set equal to 0. But I can definitely tell that, x and y would both be positive, and the multiplier on x is 1/16, and if this negative y squared was on the other side, it would have a coefficient of positive 1. So the coefficients are not equal to one another on the squared terms, so that would produce an ellipse. All right, and the next one, everything's a little bit more written out. It's set equal to a constant. And in this particular case, the multipliers on the x squared and the y squared are equal to one another. So that's going to be an indicator for a circle. And then, lastly here, the coefficients on the x squared and the y squared are -3 and 2 respectively, which are not equal to one another, but also one of them is negative and one of them is positive. So that's a situation where we have not an ellipse, but a hyperbola. All right, so that should help you understand the differences there. And of course, it is entirely possible that some of these might not actually produce a conic section because it might be something that's a degenerate figure, or it might be something that is actually non-real, but these would be the best indicators without further analysis. So just kind of examining those coefficients, these are the best choices we can make.